Hi, my name is Alexis, and today I'm going to be presenting Hooke's Law alongside of Sarah and Anna. Hooke's Law is a principle in physics that describes the behavior of elastic materials such as springs when they are stretched or compressed. It states that the force required to change the length of an elastic object is directly proportional to the amount of deformation as long as the material's elastic limit is not exceeded. This relationship is expressed by the formula F equals negative Kx. Some relevant fields to Hooke's law is materials science, which helps us study stress, strain, and elasticity to determine how strong or flexible a material is. Engineering, mechanical, civil, and structural engineering. It's used to design springs, bridges, buildings, and machinery. Physics, fundamental to understanding forces, motion, and the behavior of elastic materials, as well as biomechanics. We use Hooke's law to analyze how tendons, ligaments, and even bones respond to force. And here is Robert Hooke himself. He was a 17th century scientist, best known for, obviously, Hooke's law. But he was also a pioneer in biology, even being the first to coin the term cell. And Hooke also contributed to astronomy, architecture, and engineering, helping rebuild London after the Great Fire of 1666. And he even invented tools like the balance spring for watches. And his work really laid the foundation for many areas of modern science. In his original experiment, Robert Hooke studied how materials, especially springs, responded to force. He would attach weights to metal springs and carefully measured how far each spring stretched under different amounts of force. He used simple tools like rulers and scales. He observed that the extension of the spring increased in direct proportion to the weight applied up to a certain limit. So some of the challenges that Robert Hooke faced was limited technology. During the 17th century, scientific instruments were very basic, so he often had to design or modify his own equipment to conduct his experiments, which made precision a constant challenge. He also was in fierce competition with Newton, and often found his discoveries challenged or overshadowed by Newton, which complicated his ability to receive proper acknowledgement. And just accurately measuring small deformations without the modern tools was a major obstacle. Since his law dealt with very small changes in material length under force, measuring these tiny shifts without the benefit of microscopes or electronic sensors required patience and ingenuity. Robert Hooke had a strong interest in mechanics, particularly the forces in motion that govern the behavior of physical objects. His work extended to the study of materials' responses to forces, elasticity, or the ability of materials to return to their original shape after being stretched or compressed. It was a natural topic for Hooke to explore given his interest in understanding how materials behaved under certain conditions. Some of the original benefits of Hooke's law was it provided a fundamental understanding of elasticity and the behavior of materials under stress. It also explained, obviously, how forces applied to objects like springs could be measured and predicted, which was crucial for the development of early mechanical devices. Specifically, actually, the printing press, which obviously we know was a big deal in the up-and-coming years, and his law very much benefited the printing press, as well as clocks and bridges.
Hello, my name is Anna Aguilar, and I will be following up Alexis with the modern experimental process of Hooke's law. Modern-day experiments often incorporate advanced tools and methodologies to enhance precision and applicability, such as stress-strain testing machines, simulation software, seismology applications. An example of a modern-day Hooke's law experiment would be the Hooke's law and spring potential experiments. And this includes the PASCAR high-resolution force sensors, which allows ability to take direct measurements of force for each compression of the spring. The setup for the experiment consists of attaching the high-resolution force sensor to measure force, The motion sensor tracks position and speed of spring's movement. The pass car is to measure kinetic energy, and the graph, also the force versus stretch graph, where the slope represents spring constant and the vertical intercept reflects initial loading force. The procedure is to compress or stretch the spring and release. Calculate the kinetic energy gained by the pass car using motion data, and compare the pass car's kinetic energy with potential energy lost by the spring. So this modern experiment does have differences to the original experiment. The high-resolution force sensor streamlines the measurement of forces in the spring, providing direct data without needing of mass to force conversions. This appears to using a hanging mass to apply force. Energy changes are easily measured and very visual. Hooke's law remains a cornerstone in modern science and technology. It is used to understand the strength of material before using various engineering purposes. Some examples are the spring-based shock absorbers. They utilize the Hooke's law, with coil springs compressing to absorb shocks and vibrations with uneven roads. The mechanical watches and clocks use Hooke's law and their balance wheel mechanism, where a balance spring oscillates with the wheel. Sports equipment like trampolines rely on Hooke's law for elasticity and balance. And also in architecture and engineering, Hooke's law provides a description of any system that undergoes oscillations. Engineers apply Hooke's law to control and adjust the wobbling of skyscrapers and tall buildings. Biologists use Hooke's law to understand nanostructure. Taking a look into the future of Hooke's law, future research into Hooke's law aims to explore its applications in advanced materials such as fiber-reinforced composites, focusing on its behavior and under finite plastic deformations. These studies can revolutionize material science by improving the strength and flexibility of composite materials, enabling innovative engineering solutions. Hooke's law sets the stage for breakthroughs in areas like construction, aerospace, and biomechanics. Here we have an example question involving Hooke's law. You place a 2-kilogram bag of sugar on a kitchen scale that operates with a spring constant. The spring has a spring constant of 500 newtons per meter. How much does the spring compress under the weight of the bag? This question directly applies to Hooke's law, which states that F is equal to Kx. F is the force exerted by the spring. K is the spring constant. X is its displacement or compression of the spring. In this question, we are solving for the compression of the spring. The weight of the bag has to be converted to force, using F equals mg to accurately be plugged into Hooke's law formula. The spring constant is again 500 newtons per meter. This question connects the gap between Hooke's law and everyday scenarios. Working through a problem helps familiarize variables such as which is which, such as the spring constant, the force, and the displacement. It also helps us visualize force and displacement. We understand that applying a force results in a measurable change. We understand spring stiffness and how it controls the relationship between force and displacement. There was a process for writing this question. First, we identify the concept, which is Hooke's law. It has interaction between force, spring, and compression. We identify what the focus will be, which is what we're solving for, and is the compression. Define the known variables, which is mass of the bag and the spring constant. Define the unknown variables, which is force and displacement. And then identify the added formulas needed for the completion of the Hooke's law formula, which is finding the gravitational force. And we realign the formula including all variables to solve for x. This question establishes a practical connection between the principles of physics and everyday life. This question necessitated the inclusion of an additional formula, which is F equals mg, to determine the force, which is essential for applying Hooke's law. The initial Hooke's law equation required rearrangement to isolate the displacement, x, as a variable to be solved.
Okay, hi, I'm Sarah, and on this slide, we're looking at two things. First, on the right side is a force versus extension graph. This graph shows us that as you apply more force to a spring, it stretches more. And you can see it's a straight line, which shows that force and extension are directly proportional, which is exactly what Hooke's law tells us. The slope of the line is the spring constant, which is basically how stiff the spring is. And then on the left side, we have a diagram of a spring. The top part shows the spring at its normal unstretched length, and when we add a force, it stretches, and that stretch is called the displacement, or x. The arrow labeled F shows the direction of the force being applied, and this helps us visually understand how force causes the spring to stretch according to the formula F equals K times X. On this one, We have spring constants and variables, and the spring constant, which is K, it tells you how stiff the spring is. It is measured in newtons per meter. Bigger K, or spring constant, equals stiffer spring. The displacement, which is X, it shows us how much the spring stretches or compresses from its original length. It's measured in meters, which is M. And a positive X equals stretched, and a negative X equals compressed. And a cool tip is, the bigger the spring constant, the harder it is to stretch the spring. Alrighty. And on this slide, we are solving the problem from the section 4 using Hooke's law. So we're placing a 2 kilogram bag of sugar on a kitchen scale that works with a spring. The spring has a spring constant of 500 newtons per meters. The question is, how much will the spring compress? So first we use the formula for weight, which is F equals N times G, which would be 2 times 9.8, which equals 19.6 newtons. That means the spring feels 19.6 newtons of force from the weight of the bag. And by the way, a newton is just a unit we use to measure force. Now we go to Hooke's law, which is F equals K times X. But we're trying to find X, the amount the spring compresses. So we rearrange the equation to solve for X, which is X equals F times K. X equals F divided by K. So we just divide both sides by K to get X by itself. And so now we just plug in the numbers, which is X equals 19.6 divided by 500, which gives us 0.0392 meters. So the spring compresses 0.0392 meters, or just under 4 centimeters. That makes sense because the spring is pretty stiff, so it only moves a little under the weight. This example shows us how Hooke's law helps us solve real-life problems, like predicting how much the scale spring will move when we add weight. So on this slide, we're checking the solution with Hooke's law. So Hooke's law, is just a reminder, is F equals K times X. So we calculated the weight, which is the force, to be 19.6 newtons. The spring constant, K, is 500 newtons per meter. So using X equals F divided by K, we found X equals 0.0392 meters. And why the solution makes sense: the spring only compressed a small amount because it is very stiff. It's 500 newtons per meter. A small object, like 2 kilograms, would only cause a small compression, as Hooke's law predicts, and the compression is directly proportional to the force, matching Hooke's law behavior. So just a few fun facts. Robert Hooke was actually more than just springs. Robert Hooke is famous for Hooke's law about springs and elasticity. He was the first to use the word cell after looking at plant cells under a microscope. Hooke and Isaac Newton were rivals. Hooke accused Newton of stealing his ideas. After Hooke died, Newton made sure Hooke's name was mostly left out of credit. Hooke helped design parts of London after the Great Fire of 1666. And he wasn't just a scientist, he was also an architect. So how does this topic connect to us? So this topic connects to real life in more ways than you might expect. I'm into physics because I want to become a cardiac sonographer, which actually uses physics every day. We use sound wave physics like reflection and the Doppler effect to create images of the heart and measure blood flow. Hooke's law is part of the same kind of thinking. Understanding how forces in motion work helps in medical imaging and diagnosis. Even outside of healthcare, this stuff is used in engineering, construction, and designing things that move or stretch. And so just a couple of things that we learned as a group. We learned that Hooke's law explains how the force needed to stretch or compress the spring is proportional to the amount it moves, which is F equals K times X. It's important because it helps us understand how materials respond to forces. Sometimes that's used in physics, engineering, medicine, and more. Our group learned how to apply Hooke's law to real-life problems like measuring spring compression and saw how it connects to careers like cardiac sonography. We also learned some cool history about Robert Hooke and how his ideas are still useful today. And here are just some of our sources.